Great. So I really appreciate your time this morning. My name's Reid Priedhorsky. I'm a scientist at Los Alamos National Laboratory. I made this photo about a block from my house, and I live in a pretty mundane part of Los Alamos. So the point there is that we are hiring. So I thought we could spend the next half hour talking about these things. So we have a thing called user-defined software stacks. I'll explain what those are, get into the motivation for containers, and then our solution is called CharleCloud. And then finally I have an actual demo that I will run for you. So the premise here is that some people need different software. So on HPC systems, the software stacks that the admins tend to put in by default are good at specific things. And for us, that's MPI-based simulation codes. We're quite good at that. But if you have something that's different, for example, you have a simulation that's not MPI, data analytics and machine learning is something we've been talking a lot about here. Or if what's different is that your build process is insane, we can help. And so the sort of orthogonal issue is that the admins are very happy to install software for you. But the trick is that that software needs to have enough demand to do it. If you have an unusual need, it's likely to go unmet. And the question is, are you crackpot or innovative? And it's not always obvious beforehand which of those it is. So the solution that we're calling user-defined software stacks is basically bring your own software. So what we want to do is let users install software of their choice, up to and including a complete Linux distribution, and run this image that they've created on compute resources they don't own. It's stuff that we own. Why might you want to do this? The advantages we see, there's basically 4 categories. So if your software has dependencies of some kind, so this is maybe there's a lot of them, they're strange, they're older than what's on the machine already, they're newer than what's on the machine already, you need the internet to build. That's common in some systems. Portability of environments. So say you want exactly the same software environment across your development, testing, your smaller clusters, your larger clusters. Consistency of environments is related. So many fields of study have a specific validated software stack, and you can't get published if you don't use that stack. For scientists like myself, that's important. Various standardized environments, and also archival environments. So you want to run your code, and sometime in the future you want to come back and you want to run it again using the same environment. That's what we mean by archival. And you can also, by doing the UDSS stuff, you can get greater usability to accomplish the previous things. Now, of course, there's some possible drawbacks, which is what makes this not an easy problem. So HPC centers, we've worked very hard and spent a lot of money to have specific functionality that makes us interesting and special, different than business data centers. And that's things like our high-speed interconnects, accelerators, parallel file systems, things like that. Performance. So there's lots of opportunities to introduce overhead, which you want to avoid. And these sort of motivate our design goals. And we've identified 3 specific design goals for a UDSS solution. One is that you want a standard reproducible workflow. You want it to work well on existing resources and be very simple. So expanding that a little bit, basically what we mean by standard and reproducible is that's in contrast with tinker around until you're happy and then freeze your environment. Standardized workflows that reduces training and development costs and increases skill portability. And then reproducible basically means that you can make your images more easily and the process is more robust. Working well on existing resources. So HPC centers are very good at what they do. We want to continue with that. And we also, so we don't want to re-implement and re-optimize the things that we've already done. So things like resource management, HPC has solved those problems. We've got all these different schedulers. File systems, we have lots of very performant file systems. We've got high-speed interconnects. People have been talking about InfiniBand and OPA at this meeting. And then finally, we want to be simple. Why do we want that? We want to save costs, and they come in lots of different dimensions: development, debugging, security, which is something we think about a lot at Los Alamos. We're actually very good at it, in contrast to what you hear in the news sometimes. And then usability. And this is in keeping with the Unix philosophy of make each program do one thing well. So some options. We see basically 3 options for getting into user-defined software stacks. I'll just have a table right here. So one is compile it yourself. This is basically you download all your dependencies, you compile them, you share most of the stuff with your native host system. Advantages is that this is available almost everywhere. You can do anything in principle. Of course, in practice, this is getting very difficult, which is limiting. Virtual machines, I'm sure folks here are familiar with virtual machines. This is sort of maximum isolation. You share very little of the native host. It also gives you a lot of flexibility. On the other hand, this is a pretty heavyweight solution. We've implemented prototypes in my group, and there's a lot of infrastructure you have to put together to make this work. And the other piece is, so this is kind of a question that hangs around here. Should HPC be more like the cloud? My own opinion is, no, we shouldn't, because we're good at what we do, and we don't want to re-implement and re-optimize. So there's this middle ground called containers. Basically, this is you isolate your user-defined stack using kernel mechanisms. So you share the kernel with the host, and everything else is within your user-defined stack. This is pretty easy to manage. You get good performance. Your flexibility and isolation are sufficient, which I think is the right bar. And then the drawback is that this is newer, and so you run into some issues there. We think that for HPC, this last one, containers, is the best approach, generally. So then there's lots of container implementation out there. We sort them into basically 2 bins. One is what we're calling full-featured. So there's a lot of different things that container implementations can do. So you can build your images, you can manage them. Sometimes this gets fairly hairy, specific backend storage drivers, et cetera, storage management, runtime setup. So this is things like, do you work like an inetd? Do you have a default script? Stateful containers that you can start and stop, daemons that do various supervisor stuff. And these are some of the implementations that we're aware of that we classify as full-featured. So Docker is very famous, of course. In the HPC space, what we hear a lot about are Singularity and Shifter. Singularity is the one with the S and the 4 colors. And Shifter is the gear shift thing. So these features are useful. They were implemented for a reason, but because there's lots of them, there's drawbacks. So one is code size. You got a big system, you have to support it. That's a cost. And they tend to involve privileged and or trusted operations, which certainly at Los Alamos gets us a little excited, and I hope that it does for you too. So there's this alternative, which we're calling lightweight containers, which deliberately have few features, and basically the way that it works is, given an image, given some image of a user-defined software stack, run some processes in that image. Implementations that we see there, so the util Linux has a command called unshare that's pretty handy. And you'll see that systemd and nspawn appear in both places, and we're not quite sure if they fall entirely in one category or not. And then CharleCloud is our solution. And basically the advantage here is this is a lower cost deployment, in our opinion, significantly so. So what we believe is that lightweight implementations are a better choice for HPC centers. They capture the most important parts of cloud flexibility, but they don't compromise the existing tools and strengths of HPC centers. But of course, some of these features are important. And this brings us, not quite. So there's lots of ingredients to containers. So I wanted to talk a little bit about that side. So sort of the key part is Linux namespaces. So what this is these are per process views of different kernel resources. There's 6 of them. So you have mount, which is the file system tree, and the devices that you have mounted. You have process IDs, the host name and the domain name, all the other network stuff. Those are 2 separate ones. IPC, this is shared memory and things like that. And then user is your current UID and GID and capabilities. There's several other ingredients as well. So you have C groups. This lets you put per process limitations. PR control, no new privs is actually kind of interesting. Basically, this removes the ability for that process or any children to escalate privileges basically in any way. So if you do this, your set UID binaries won't work anymore. You can filter system calls with setcomp, and then there's things like SE Linux and AppArmor. In our opinion, the namespaces are sort of like the key to it, and the way that you manipulate them is with system calls. You can write a program that does these system calls, and now you have namespaces. And there's 2 types of namespaces. So one is the privileged namespaces, which is the first 5. And this is basically you have to already be root in order to create namespaces in this class, unless you add the unprivileged namespace, the user namespace, into the mix, in which case you can do the other 5 without being root. And in our opinion, this is the key. These 2 get you to a lightweight container implementation. Which brings us to CharleCloud. So this is our director, Charlie McMillan, who's retiring. So I mentioned that Los Alamos is hiring. And we're taking a hybrid approach. So part 1 is that image building and image sharing goes into a sandbox. So this is a safe place for users to be root, i.e. not on my system. And that could be things like a user workstation or a virtual machine. Currently, what we do is we wrap Docker for image building. But the important part here is that we want a file system tree that looks like a Linux distribution. So that could, other stuff would work too. So that's things like dbootstrap. You can do yum install root. If it looks like a Linux file system, we can run it in CharleCloud. And that hints at the other part of it. So we run images with our own unprivileged runtime. So we use the mount and the user namespaces to accomplish the unprivileged part. To do this requires a somewhat new kernel. So somewhere, it's a little fuzzy because it wasn't just like dropped in, then it works. It's like they dropped it in and like it sort of matures over a little while. So we've been happy with 4.4 is what we run now. Things like 3.8 and 3.10 are too old. The thing is that most distributions have the right kernel. Cray up 04 has it. Red Hat and CentOS does not come with the right kernel, but you can install it by other means, EL repo being one of them. And the key thing here is that the unprivileged runtime is just a user program. Admins don't need to do anything to install it, anything special. I mean, if you want to install software, that's fine, and it's more easily available. But if you have kernel support, users might be running CharleCloud and they won't even tell you, which is cool because you have less work. The performance question is an important one. So I'll just touch on that very briefly. So CoMD and VPIC are 2 science codes. We did some experiments comparing performance of bare metal and CharleCloud, and the conclusion is that the performance is basically the same. So it happens in this slide that both of them we're a little bit faster. We're not making that claim. What we are claiming is that it's about the same, which is what we expected, since you're basically using all the same stuff as your native stack. Same kernel, same devices. So the basic CharleCloud workflow has 6 steps. So one step is build your image of somehow, Docker being the currently supported way. Put that image into a tarball. Copy that tarball to where you want to run. And note that this is a tarball, which is a file, which everyone knows how to handle. Unpack the tarball. Sometimes you need to configure some stuff, and then you run your commands in the container. In the where column there is where this is taking place. So you can see that some of it is happening in Sandbox, some of it is happening over on the production side, and only those first two steps are privileged. It says maybe because if you're using Docker, yes, those are privileged steps. If you're using some other method, maybe they're not. So let's do a demo. So I've got a terminal here. Let me just size that to something reasonable. Okay, so obviously I'm using a Mac. This is a virtual machine running in VirtualBox. So whoops, -A. So this is a Linux virtual machine right here, and this is one of the demos that comes with CharleCloud. So CharleCloud is open source. So we're going to go in the source code, examples. We have some MPI examples, MPI hello. Okay, so what do we have in here? There's a few files. We're going to look at the Docker file first, because we're going to build this using Docker. So the cool thing about Docker files is it's a very specific list of steps to build your image. So at the top here we have from Debian and Jesse. This is my opportunity to play with Debian, which I really prefer to Red Hat, which is not the consensus in supercomputing. We're going to install OpenMPI inside this, this container. So we get our build environment here with the OS packages. We download and compile OpenMPI, which is this stuff here, and then this example. So the root of this path here, examples MPI hello. This is relative to what Docker calls its context. So we're going to offer a bunch of files to Docker. We're going to copy some of them into the image. We're going to cd into hello, and then we build our application. You might say, okay, well, what is that little application? This is just basically an MPI test program. So we're going to report our user namespace and rank, then send some messages and like say, okay, it worked. So it's not very long. You know, this is how we figure out what namespace we're in. You know, initialization, send some messages, etc. And then at the end, we're like, okay, finalize, okay. So ch build is the it's a wrapper for Docker build, and basically it puts the environment together in the way that is tidy. One of them being proxy, so we can do ch build. Oops. Says create a Docker image tagged MPI hello. This is the root of the CharleCloud source code. This is the context, and all the examples are written at the root of the source code is the context directory that's expected. So this will build our image, and you can see that there is a fair amount of output here. This is a hot cache, so Docker built it really fast. And you can see that these are the steps that we had previously specified. Now what we're going to do is we're going to dump the tarball. So I say docker to tar. Here's my Docker name, and then please put the tarball in var temp. So this is the one where it actually has to think for a little bit. This is wrapping the Docker export command, which gives you a tarball. So we have our little tarball there. It's pretty small. This example is pretty tidy. So now what I'm going to do to prove that we don't need Docker anymore is I'm going to kill the Docker daemon. And then what we do is unpack the Docker, or unpack that tarball. MPI hello. Okay, so that's the tarball. It goes into var temp MPI hello. This is just a wrapper for tar xf, and it does a little bit of little bit of sanity checking. For example, it excludes /dev from the extract. Some distributions like to put device files in /dev, and you can't unpack those as a normal user. And so this prevents you from bumping into that error, for example. So we'll do that. It happens that I did practice this demo, so that's why it's replacing the image. And then it says var temp MPI unpacked hello. OK. When we run this on our big systems, you would do srun unpack, and then it does it once on each node, and we put it in a temporary directory that's per node. So what's in there? It looks like the root of a Linux file system. If we do if we list everything in there recursively, we can see that it's about 18,000 files. So it's a Linux file system. So now we're going to start to get into the actually running it. So var, or not, that's not var, it's proc self ns. So this lists my namespaces that my current process has. And so the thing about namespaces is that you always have them, whether you're using them or not. And then chrun is the key command to actually enter your container. So I'm telling it the image, which is just a directory. So we'll do this inside. The color never, that's just, these are symlinks, but they don't point to real files, and ls likes to blink in that case. So if we look at the mount namespace, those numbers are different. The user namespace, those numbers are different. Everything else is the same. And that's because we picked those two namespaces as the key. So if we then do, we're actually going to run our hello world program. We can do it in two ways. So we can do MPI run. Let's say we want 8 processes. And hello is the, that's the executable that's inside the container. So great. We have 8 MPI ranks. And notice that all of them report the same user namespace. They're all running in the same container. We can do it a little bit differently and use the host's MPI run. And this is how you would do it when you're running it on a cluster. Oh, and I didn't do the NP8, but you can see that this one, now we're running each MPI rank in a different container. But because they still have the same IPC namespace, they can talk as if they were just running on the native system. So that concludes our brief demo. And it worked, so I'm going to skip all the backup slides. The disadvantage is you don't get to see those cool cat pictures. Okay. So we can compare it to our design goals. Standard reproducible workflow, we use Docker. That's an industry standard. Or if you want to script up something else, that'll also give you reproducible workflow. Work well on existing resources. So chrun is this minimal but sufficient isolation using the mount user namespaces. Performance, no change, direct access to everything. Scales using existing standard HPC tools. So you can run big apps using MPI run across your cluster. You can do that in CharleCloud too. And it's very simple. So we got a few shell scripts, 2 C programs, 900 lines of code. If you look at some of the other implementations, they tend to be much larger. So NSGL 4,000, Singularity 11,000. I actually think that one is much more because Singularity adds lines of code very fast, and Docker is another beast. So status. It's available now on some Linux LANL clusters. Passes tests on the craze. Something that I thought was kind of cool is I went from never having touched one of our craze to passing almost all of the CharleCloud tests in 2 hours. I thought that was cool. You can install it on any Linux box. You need a newer kernel. Or you have to be willing to tolerate a setuid binary. You actually can build that, and that will let it run on pretty much any reasonably recent Linux kernel. Works on the cloud. You saw that I used a VirtualBox image. We are almost ready to put instructions on the web for building that image, so you can take about an hour and get it, maybe half an hour and get it running. Very easy. That'll also let you run it on lots of different types of systems. Yeah, so if you would like to learn more, here's a few other resources. So we have an article appearing in Login very briefly. Next month, ask me if you'd like a preprint. We have a supercomputing paper. If you Google this tech report number, you can read our preprint of that. Documentation is on the web, and it's open source, so you can download it from GitHub. Thank you.
Any questions?
Hi, just a quick question. Do you advise for running on clusters to first unpack everything from the container and then submit the job, or submit the job and as part of the submission is unpacking the container on the compute nodes?
The way that we do it is that you unpack it as part of the job, and this lets you put an image into local storage on every node, which makes it, basically improves your performance. We use just a tempfs for that. Even relatively hefty images are about a gigabyte. You know, image around a gigabyte takes a few seconds to unpack. The advantage there too is that you hit your shared file system for one file instead of lots of files. Now in principle you could unpack it once and then run it against each node looks at that same image. Right. So they'll see the same container in either case because you've unpacked the same tarball. We do, CharleCloud mounts the image read-only, so it is consistent in either case. Right, but they're doing it all in parallel, so it's pretty fast. Yeah. Other questions?
Great, thank you very much.
Thanks.